Is it okay? Yeah. Okay, so my name is Stefan. Thank you for coming actually to the workshop. And I'm going to present to you now some stuff about system building and how we can do this with HTMD. I think there will be some overlaps with what Tony presented before. He presented very nicely the molecule class, which we are going to use here as well. So, but doesn't matter if we repeat some stuff. So I'm first gonna talk a bit about, well, very quickly about system building. Then I will show you what tools we have in HTMD for building systems. The typical workflow that you need to do to prepare a system. Then I'm going to show two examples, ligand binding methionine trypsin, then a receptor which is inside the membrane. And the last part, so the last half an hour, we're going to do a hands-on example, which is in the exercise folder, and you can solve it yourselves. And we will go around and help you. So Gerard also and Noelia, if she's here, they can help you with the exercise later. So when we want to build a system, essentially we want to prepare our kind of simulation box for simulation. So we start with some molecular structures. We want to modify them, position them correctly in the way that we want, and combine exactly all of the molecules that you want into one system. And all of this, you want to do it for a specific force field. So usually we use charm, or you can also use the Amber force field. The idea that we had when we were doing system building for HTMD was that the building process should not depend on which force field you are using. So it should not depend if you're building for charm or for amber. You'll do the same commands, and as the last command, then you can change between the force fields. So that allows you to, first of all, build for various force fields without any changes, and second of all, you can, if you want to test different force fields, for example. Here we're just going to work with charm. So the various tools that we provide. So before we showed you the molecule class and some of its methods. There are actually a few more methods for the molecule class. In general, you can also check the documentation online on the HTMD.org website. So there you can see all of the methods of the classes. So the extra methods that we're going to use are the append method, which combines two molecules together. The center method, which moves the geometric center of all of the atoms to the 0, 0, 0 position. Mutate residue, so if we want to mutate a residue. The move by, rotate by, I think Tony already kind of showed you. So you take a selection of atoms and you move them to some other position. Or you rotate a set of atoms, and the rotate, I think you can provide your own. No, one of them, the rotate by, you provide a rotation matrix, and to the rotate, you can rotate around the specific axis that you want. Then there are some extra functions which are not inside the molecule class, but they apply to the molecule class, which we're going also to look at in a second. But okay, so there is one, the max distance, which calculates essentially the maximum distance of all of your atoms from a specific point. The uniform random rotation, which we will use to rotate something randomly. The bounding box, which takes a selection of atoms and tells you what the bounding box is, so the tightest box that you can fit around it. The sequence ID we will not look at so much. The embed function, which is very useful if you want to embed, for example, a protein into a membrane. The segment gaps, which detects the gaps inside the molecule when there is a change in the res ID, for example. Then the solvate, which we will use to make a solvation box, and the charm and amber functions, which are used for building. So the typical workflow that we do when we build a system is we obtain the structures, usually from the PDB. Then we do some cleaning. We remove ligands. We remove, like if there are trimers, we keep only one of the chains. The third step is to define the segments. So this, Tony also mentioned a bit about segments, and they are very important in building. So especially proteins, especially for proteins, if you have multiple chains, they should be defined as separate segments. If they are inside the same segments, the protein, the building process might try to bond the two chains together, and so you should be careful about that. So during this building tutorial that I will show you, we will be defining segments all of the time to different molecules so that we are sure that there are no problems there. the waters inside the water box can actually all be inside the same segment if you want. That's not a problem because the building methods will recognize them and split them correctly. And the same thing applies also for the lipids, but not for the ligands and proteins where you need to separate the segments. Okay, so the next step would be to combine all of your structures together. If you have a ligand, the protein, your membrane, you combine them all together into one single structure, which you then solvate with a solvation function, which puts it all into a water box. And finally, you build it and you ionize it for a specific force field. Okay. So the first example that we're going to do is benzamidine trypsin, and I actually realized that that's not benzamidine in the figure. I got the wrong figure. It doesn't matter. You will see it anyways once we start building it. Exactly. So you can follow this on your machines and execute all of the cells as well. This code. If you are in presentation mode, you have to execute the first cell, which imports HTMD. If you haven't done it. Okay, so first of all, okay, we have a folder called bentrip. Inside that folder, we have the trypsin PDB, which is our protein. We have the benzamidine PDB, which is our ligand, and then we have the RTF and PRM for benzamidine. These are the parameterization and the topology files for benzamidine, which are needed to be able to build the system because the parameterization for benzamidine is not known. Okay, so the next thing that we're going to do, you can either, as Tony told you already, give a PDB ID here, which is again the same protein actually, the 3PDB. Or you can load directly a PDB file like this, and we can view it inside our nice NGL viewer. Exactly. Also for the NGL viewer, we didn't show you, but you can double click on it, and it goes into full screen mode. And you can also click on atoms, and here what I wanted to mention about clicking on the atoms, you can see here after this column, the letter is the chain ID. You're going to need it in the exercise. This chain ID, that's when you click on an atom, it tells you which chain it belongs to and the name of the atom and the name of the residue and so forth. Okay, so double click again. No, sorry, I wanted to talk to you about this. So the structure, as we see, it contains a protein. It contains the benzamidine ligand bound inside the protein, and it also contains some crystallographic oxygens here. The oxygens you can either keep or remove, but I think we're going to keep them in this case since they're useful. So, I mean, you could remove them because we will solvate everything in a water box, but you might want to keep the specific positions of the waters that were already identified by the crystallization. So we want to clean our structure. So we have two ways of doing it. We can either filter the structure and only keep something in it. In this case, the chain A and the protein or water. And then, there's also a calcium ion, which I didn't see before, actually. Here. The bonds that it shows sometimes in the viewer, they are not real. So these bonds, I think, are not real. They're just guessed based on the distance. So don't trust too much the bonds that you see here. You can actually disable the bonding. If you put here guess bonds is equal to false, it will disable the bonding, but then it will look also a bit uglier. So, okay. So let's filter then our protein. Let's remove, so we want to remove the ligand because we have benzamidine bound already inside the pocket. We want to start our simulations with benzamidine in the water and then see the binding events. So first we remove the ligand in this case, either like this or with the remove command, which is, I guess, cleaner because you remove directly the res name ben, which is benzamidine. If I call this here, you probably see, if you see the output, no, you cannot see it now due to the size, but one moment. It will tell you that nothing really was removed because we already removed it before with the filter command. Yep.
Do you do anything about histidine, glutamine rotations?
No, I think that the system building itself doesn't. No?
Well, you know, the B files open, they're rotated the wrong way. And you can...
No, we don't check that.
At the moment, but the idea is that it's already from A inside, and we will check the automation and be a more advanced building system in the future that check.
Yes, yes.
cases or
So for the moment, yeah, it doesn't check for that stuff. Exactly, okay, and the res name CA was for this calcium ion that we wanted to keep. Okay, so now we need to define the segments, our segments. So we'll define one segment here with, 1 second, I'm gonna zoom in a bit more. Okay, the first command will define all of the protein into the segment P. Second command defines all of the waters into segment W, and then the calcium ion, we're gonna put it by itself in another segment CA. Okay, once we run it, there is no output, but okay, it modified the protein, the molecule, sorry. And then we're going to center all of the protein and put it to the 0, 0, move the geometric center to the 0, 0, 0 coordinates. It's not necessary, but I think sometimes it's a bit easier to work with if you move everything to the 0. So let's add our ligand now. So since we have the ligand already in the benzamidine.pdb, actually before, even if we didn't have the PDB for the benzamidine, we could have gotten it out of the previous structure by using the .write command. So we could have done mol.write and written out only the benzamidine into a separate file. So now we load benzamidine back in as a separate molecule. We move it to the center, and then we just visualize it here. And okay, yeah, and it's, as we can see it here. So there is a problem now, obviously, because I moved the protein to the 0, 0, 0 position. Now I move the ligand as well to the 0 position, and we've got the ligand stuck inside the protein, which is obviously not ideal, since that's probably going to crash our simulation, and it's definitely not going to bind. So let's fix that. So what we want to do is we want to reposition the ligand, and what we really want to do is to position it essentially in a sphere around the protein. So you have your protein here, and you want to put it randomly somewhere in a sphere of a specific radius around the protein. So what we're going to do is we're going to calculate first how large the protein is, kind of its radius of gyration. So using this max distance command, it's going to tell us what the furthest atom is from the 0, 0, 0 position. So in this case, if we run this command, it's going to print the maximum distance, which is 28 angstrom plus a little bit. So we definitely want to move the ligand at least 28 angstrom, but to add some more space so that it's not touching with the protein and that there are definitely no interactions at the beginning of the simulation, we add another 10 angstrom. So in this command here, I'm doing distance, the furthest distance plus 10. So I'm adding 10 angstrom. And as you can see in this command, I'm moving the ligand only in the x dimension. So I'm just taking the ligand, let's say from here, where it was at the 0, 0, and putting it here. And now we want to rotate it. Sorry. I forgot one command. Exactly, up there. Sorry. The first thing that I'm doing up there, in this cell, is that I'm taking the ligand and rotating it around itself. So just randomize its orientation, essentially, of the ligand. And then I'm moving it like 38 angstrom, no, 38 angstrom into the x dimension, and then I'm rotating it again. And since I'm rotating with this command again around the 0, 0, 0 position, and the ligand is here, it's going to rotate essentially in a sphere around the 0, 0 position randomly. It's just going to get positioned randomly on that sphere. So this is very useful if you want to prepare multiple simulations. So typically we don't start our ligand in one position, only because it kind of has a bias that it might interact more on that side of the protein. So we prepare like 20 initial builds, initial systems in which the ligand is placed randomly around the protein. Okay, so okay, and this. Okay. Okay, let's not forget the segments. We need to put the ligand in a segment, let's say L. So these you can freely choose as long as they are 3, I think 4-letter codes are also working in SegIDs. And we're going to call it mol in this case. We could have left it as Ben, but mol, I preferred it in this case. Okay, so now we're going to combine all of the protein with the ligand that we have into one single molecule. So we create an empty molecule. In this case, I also gave a name This name is only useful if you use VMD to view the structure. It's essentially your molecule name in VMD. So in this case, it's not going to do anything. This name argument that I gave to the molecule constructor at the beginning. And then I'm going to append the protein. I'm going to append the ligand, and then add some representations and view it. You might notice that I'm using a bit of a different syntax for the representations than Tony. So I'm not passing the representations directly to the view command with a hold on, because these representations that I add, they will kind of stick with the molecule. So every time that I visualize this molecule, we will see the same representations. If you give the representations just to view with a hold true, then they get deleted after the last command, the representations, and you would need to give them again. So in this case, because I wanted the representations to persist, I added them like this. Okay, and we can see that the ligand is now located perfectly far away from the protein, and the protein is there. And well, I forgot the representation for the calcium ion, but it's there. Okay, so now we want to solve it. And okay, obviously, since we moved the ligand away, we want even the ligand to be inside the water box, so we add a bit more of a buffer. We add another 5 angstrom around the position where we put the ligand. And we're going to solvate with this method here, the solvate function, which takes as a first argument your molecule that you want to solvate. And in this named argument here, it has lots of arguments, different arguments for solvating, but the one we typically use is min max, which defines essentially the min XYZ dimensions and the max XYZ dimensions of your box. So in this case, we're just going to define the minimum as the minus d minus d minus d, since this d is the distance, it's kind of the size of the protein plus the 10 angstrom, so the ligand plus 5 for the box. And plus d plus d plus d. And since our protein is centered on the 0, 0, 0 position, it's going to create a box around it of 2d size in each dimension. And the second command, okay, just adds a representation for water so that we can see it. And let's execute it now. Okay, so we see that there is a progress bar here for solvating, and that it and it should visualize soon. It takes a bit longer to visualize because it has all of the waters, so the NGL viewer takes a bit longer. Okay, so now it looks very nice. Everything is, oh, actually, no. Okay. I think I might have done something with the D's wrong before because I was running the cells a bit wrong, but in your case, does it look fine? On the... Yeah, okay. In any case, in the worst case, you can just add a bit more size. I think I might have done a mistake here during the process, but... Okay, so now since we have everything essentially inside our water box, we want to solvate it. We want to build it. So, is it working for you, or is it the ligand outside the box?
You have to add the 10 for the ligand.
Ah, okay. Ah, yes, you're right. Okay. Okay, yes, I actually did just plus 10 when I used it, and I didn't sign it. Okay. So if you want to correct it, the mistake was here that I didn't do d is equal d plus 10. I should have done actually d plus equal 10 and then used d here. Okay. And if I had done this, everything would have been perfectly inside the water box. Actually, I might even, well, I don't know. Sorry? Yeah, as much as you want, but yeah, I mean, the extra 5 are going to get added here anyways. Here I'm adding another 5. Okay, so if we want to build, we need to kind of decide on which version of the force field we want to build. By default, we use, I think 22 star for the proteins and 36 for the rest. But here you can, if you use this charm.list files, it will give you all of the default files that we have for the force fields that you can provide to the building to use. Okay, so in the next slide, we're going to build and ionize. So this might fail now because I failed at my salvation before. If we run it, it's gonna work, but I don't know if we have time now. But I'm gonna let it run anyways and see how it works. Okay, so here at the top we've defined that we want to use the 22 star, charm 22 star for the protein, and then we also provide a parameterization of the topology for the ligand, which are passed here as named arguments topo and param. The output here is where the build system is going to be written, and once it's finished, it's going to put everything into this mol build, which is a new molecule, and we can visualize it here with these commands. So what you're seeing here is the output of the building process, where it's telling you essentially that it found some bonds between the cysteines. So these are the sulfide bridges that it has found, and there are actually 6 of them in trypsin. If you have too much output, you can also click here once and twice, I think, right? A bit faster. Yeah. Well, or scroll in this case. Okay, yeah, okay. I think I failed because of the dimensions that I gave before. If you have a problem actually in building, you should check the log file, which is written into the temp build folder in this case, since I defined this temp build. The log file is there. So if you went, for example, and opened the console, if you open a terminal, you can go to, you can list the files in temp build. Okay, and here you can see the files that it produced. In this case, it didn't manage to complete because of the error that was there. But essentially, it writes all of your segments as separate PDBs, and then in the end, it produces a structure.pdb file and the structure.psf file, which are the files that you're going to use for simulating later. Okay. Okay, sorry for this. I think I just ran over the commands a bit weirdly, so I didn't manage to build it, but I think this one is going to build, I hope, since it was building at least until yesterday. So the second example that I'm going to give, I don't know how much time do I have? Till 1? Oh, okay. Okay, let's go through this a bit more quick because we have to do the hands-on example. So this is another system where we have a membrane and a protein, and we want to build that. So here we use a bit of a different process. So let's load the protein, we filter, and we keep only parts of the protein. We do the segment gaps, which identifies if there are gaps in the res IDs of your protein, and it found actually 2 of them, and it's correct because there are 2 chains inside this protein. So now if we go, okay, it identifies the gaps and it also assigns them a unique segment ID to each. So here I put P, so that means that the first segment is going to be called P1 and the second segment will be called P2. So it will add an integer after whatever string you give it here, which it will increment. So the difference here is that I'm going to build directly the protein at the beginning. The reason for that is that this protein takes some caps at the beginning and the end. If I don't build it right now, the protein, we will solvate the protein without the caps. And then when the builder tries to add the caps, they're going to crash with the waters. So it's actually a good idea to directly build the proteins at the beginning, like in this case, so that you, without any water and without ionization or anything, you just build it, let it run for a second, and then you view it. So perfect. Now we can see that we have our 2 chains here, the black and the red chain, which are the 2 segments of the protein. Now we want to add the sodium ion to the receptor, so we load the sodium, we set a seg ID for it, we append it, and we add the representation for viewing. Okay, and now we have our ion inside the receptor. You might have needed to move it. In this case, it's positioned perfectly, but if you had to move it, you can use it with the move by method. Okay, so now we want to embed the protein into a membrane. So we're going to load the membrane. This membrane, I think, was created using VMD, if I'm not mistaken. Yes, it's 80 dimensions. I think they are the dimensions of the X and Y, so 80 by 80. and build with for charm 36. That's what its name is for. And what we're going to do is, okay, we're not going to use a center method this time. We're going to do it a bit more manual. So we're going to calculate the center of the protein, which we do this with this NumPy mean here, where we calculate the center of the protein, then we calculate the center of the membrane, the geometric centers always. And then we're going to move the membrane so that it's centered directly onto the protein. So actually something that we didn't mention before, and we should have mentioned, I guess, is this axis 0 here. So the coordinates that are stored inside the molecule, they are essentially a 2-dimensional or 3-dimensional array. So if it's a trajectory, it's a 3-dimensional array of coordinates. If it's if it's not a trajectory, it's just a PDB, for example, it's a 2-dimensional. The first dimension, so going down, are your atoms, and the second dimension are your x, y, and z coordinates. So if I'm doing the mean on the axis 0, it means that I'm doing the mean going downwards, which means that you're going to get the mean of the x, the mean of the y, the mean of the z for all of your atoms inside the molecule. Okay, and then I'm going to use this embed command, which takes the first molecule and the second molecule, and it appends them into a single molecule, but what it does is it removes all of the clashes between the two and removes only from the second molecule. So in this case, it's going to remove lipids from the membrane while keeping the protein intact. That's what this command is going to do. And additionally, it's a bit more clever, so it doesn't just remove atoms, it removes whole segments. So if you only removed some atoms, for example, from the lipids that were clashing with the protein, then the lipids would be missing atoms, which would be a problem. So we remove the whole lipid, which has even one clash with the protein. Okay, so again, let's visualize it. So I'm adding some extra representations here with the selection of lipids, which is going to visualize as lines for the membrane. And it takes a bit longer to load since it has more atoms here, but it's fine. Okay, so here's our embedded system. So this is the membrane in lines and the protein inside. And if you look at it from the top, you can see that, okay, there is quite a gap here between the protein and the membrane. This is because we removed all of these lipids of the membrane, but if you want, you can also specify, I think, or you should be able at least to specify what the radius is of when you're going to remove what the clash is, what you consider a clash between the protein and the lipids, what distance, what the threshold distance is. So you could make it a bit tighter, essentially the membrane around the protein if you want. But this works fine, actually, in the system. So, sorry. Okay. So now we'll add again a ligand, which we have here in this folder. We're going to set its segment ID, and we're going to move it. In this time, we don't want to move it spherically around the protein because that could end up in two bad scenarios. The one is the ligand inside the membrane, and the other bad scenario would be the ligand in the extra or intracellular side. Well, on the wrong side, not the one that we want to simulate it on, whichever it is. So we're going to take the ligand and we're going to move it to a random position on a plane above the protein. So this just moves it on the x and y dimensions while keeping the z dimension fixed. So we go like at position over the protein and we move the ligand somewhere randomly there. And then we're also going to rotate the ligand in a random manner, but around itself. This argument tells you to rotate it around its own center. And then we move it, we append everything together. Okay. We solvate everything. In this case, I did the min max a bit different. So we didn't define it with this D that I was doing before. Here we calculated what the minimum x, y, and z coordinates are of your molecule and the maximum x, y, z coordinates are of your molecule. And then we add it to the z dimension 20 so that we add a bit more water on the top. And to the z dimension down, we added only 5 because we're not going to simulate the ligand in that side. So we're only going to simulate it, let's say, in the extracellular side, the ligand. So we build it, we view it, and I hope this time it built correctly, not like the previous system. Yeah, it looks fine. So as you can see, we have more water on the one side, this side here, than on this side, because here we'll have the ligand. As you can see, the ligand is also here. Well, here. Okay, so the system is ready essentially for building. So we run the command for building it. In this case, I also provided a salt concentration, which I didn't give before in the previous one. So the previous build that we did, we were just trying to neutralize. If you don't provide a salt concentration, it will just neutralize the system. In this case, it will also add the specific salt concentration. Okay, this can take a bit sometimes because this is a bit of a bigger system, but it should be done like less than a minute. I think it will have finished. Let me see what else there is while this is running. And okay, visualization, and then we are done. Oh, okay, I'm having really bad luck today. I don't know what happened. Because this was running yesterday, but something that, I don't know if it's me executing. Does it work for anyone else? Okay, so it's just me failing. No? I don't know. Well, I don't know because I guess some of them, I might have not executed some cell or something, forgotten again something during the presentation. Well, it should work. But in any case, as it says, so if you get this error, you should always check the log.txt file for errors in building, which is also useful. So I'm just going to show you that inside the folder, this time we built it in more build. So if you go to console, presentation. Okay. So inside that folder where you build the system, there should be a log.txt file which you can take a look at, and it's gonna tell you. Okay, so that's my problem. So there is no VMD installed on this this EC2 machine, so I cannot build any, not for Charm at least. So you need to have a working VMD installation on your machine to be able to build for Charm. And since I'm missing it on mine, I think it just needs a reboot. It's installed, but it couldn't find it in the path. I can fix it by quickly adding it to the. So I think the Charm build command actually allows you to specify the path to Charm. So does it work for you, actually? So VMD is installed on the rest of the machines, but this one is failing. Huh? Okay. Well, I mean, it's okay. It doesn't matter. Yeah. Okay. Well, if it worked for you, it's fine. At least we found the problem. So it's useful to look into this log file from time to time to see what goes wrong, if something goes wrong. And you can visualize it afterwards with all of these commands. So I added essentially another representation for the ions, just so that you can see the ions also inside the box. And that's it. So the rest of the time, we're gonna I'm gonna let you work on an example. So the example that we will work on is Barnase Valstar. So Barnase is a bacterial ribonuclease, if I remember correctly, and it's this. I think it's the green one. Essentially, it has an inhibitor, which is Valstar, another protein, and they bind really strongly together. They have a very high K-on. So these are just so we would like to simulate to see the protein-protein interactions in this case. So let's build this system then. So you should go into the folder called exercise. So there should be a folder here. There's a presentation folder, another folder called exercise. Okay, and there is this file here, the build. Don't open the solution yet. And open this file and try to do whatever it says here. So, okay, we have like 20 minutes, 30 minutes. I don't know how much we have, 20 minutes. So if you need help, just ask either me, Gerard is not here, Nelia. Yeah. We will go around, and if you need any help in building it, you can ask us. Yeah, I think that should be all, so that you familiarize yourself a bit with the building process. Yeah. Okay. A second. Okay. Yes. Okay, so now. Okay. Yes, did I forget at the beginning? Pictures at the beginning, the unit. So did you tell me this? The viewer. So this viewer works on Firefox and on Chrome, but only on specific versions. That's also on the newest versions. So there are some old. Okay, so the NGL viewer has some issues with older browsers and probably also more less known browsers. So with the latest Firefox and the latest Chrome, it works fine, the NGL viewer. But in others, it might not open. It might not. It might make some ugly representation and stuff like that. So. Yes, Chrome should work. Yes. Yeah, so Chrome for Linux is deprecated. They stopped supporting the new version. Or was that on my OS, on my Linux OS? Yeah, sorry. No, in general, it should not be deprecated. No, you're right. It was just on my OS. They have access. Also, in general, so when we are working on this, we use VMD. We don't use the NGL viewer so much because VMD is more powerful. The reason why we use the NGL viewer now a lot is because we are doing the presentations remotely, so we cannot start VMD. But if you install HTMD on your machines, you can use VMD then, which is a more powerful viewer. Put your viewer is equal to NGL. NGL in quotes, in single quotes. If it doesn't work, try Firefox. Yeah, give it a try in Firefox. Yeah, but you don't have HTMD installed properly. Okay, well, go to the htmd.org website and download HTMD, but it will take a while.
Yes.
You can download it by using the molecule class.
Yeah, but it's there.
Yeah, but I don't know what it is. Okay. Okay. So you can use that already when you use the molecule. So you call molecule just as fast as part. Once we go to the exercise. You have to open it. Yeah, you need to download and say that this knowledge set it all the way you start with the notebook. And now you can see that your local host So this stuff is not good when you start. You can only access any folders from where you start. So which folder would you start?
Yes.
Do you see artists now?
Losing that session as well, so sometimes the sessions get stuck. If you already tried that, then it's great. All I can suggest is try it first. I wanted to try it in my
So I only wanted one which will.
Okay, no, these two guys.
Shift tab.
Yes, you wouldn't. So, I started moving to the box and sun and love and stuff. Safety feature.
I lost it.
It should be already in your quotes. But how did you install it using Icon? Because it asks you if you want to bend it to the part.
Yes,
Ah.
we all say yes.
No, it might be because it's a bottom right hand. No, it's fine. Yeah. Now you have access to this folder. Exactly. Now you should see the files. Now you open the notebook and a new notebook. So you just go. And it creates a new folder archive. You give it the name. Good.
Display in the whole system. I downloaded it separately. Yeah, I didn't view each one next time. But I
You go one
yeah.
When you create your
Yeah. But I have to display in the whole system. Combined.
One second.
So, I just to me, it's actually it's like a trial. And that's which one is that? I'm just looking at the same protein websites, which
Yeah, actually, I probably want that. I guess so. I keep only one chain that is good. But then it's one chain. So that you get one chain from both chain, A and B. So one is like
Well, the chain
one is
is
not just
the segment unit is defined separate.
yeah, but the segment inside is not.
Yes, yeah, but afterwards you will combine. Yes, you have to.
Okay.
Exactly. So when we done want to
Because afterwards you will combine them into one more form, and then they will have the same segment.
so
Yes, segment.
whatever.
Exactly. That's fine.
Yeah, not too bad.
So at the moment, as we understand,
Yeah, but then
the HTML,
I noticed this is foundation.
so if you're doing an automated system,
I already noticed this is foundation, not one start.
Yes, but the building.
okay, but yeah,
Like if this is translate everything.
sure.
Yeah, you could put
Because the possibility is something like
I can't do that.
yeah, of course. So,
I developed this.
yeah, but it's integrated. That's understandable. Now, do you have a recommendation? I think I should stream the protein. Now,
Okay, so
the
we
other
should have the same model for the
And
particular
other question is, so there's the different
whichever one.
chains.
It would not interfere with
I normally would go there.
Yes.
Yes, also
Pretty sure you have that.
You want to know if there's several chains you just like one maybe. I mean, actually, I don't even know, but there's I don't think there's one.
none of them.
Okay, so
No, it's only the
protein.
It's a bit easier to do in DMD because in DMD you see well, we don't have KVM detection. No,
I mean, they have also curves and parts.
yeah,
Okay, so do that for the others.
exactly. You do the same for the bus, and then you also define also segment for the two waters. So for the waters of Barnes and for the waters of Barnes. And the loop. So actually here with these commands you also set the waters which were inside this, you set them also as the same. No, it's fine, because afterwards now if you change the setting with the waters, they will it doesn't matter what you put in. They will override the setting with the waters.
Is it still balance? It's not balance. It's not used in the background. It's still no.
It's installed.
So now I just set
One waters and put your W1 for example. And for the other one W2. I'll go around a bit more. If anyone needs some
If you put PDB as the is that the code? Or do you recommend to game if this means HLE, the code is HLE.
Yes, I'm not renaming them as long as the child builder doesn't change. As long as the child builder recognizes the residue, should be fine. I'm not modifying the names. So,
That might change the sequence.
Yeah.
no, if you want to, you can do the get command. Subordinates.get chain. Okay, and there's also
First shift and then that.
Yep. The NP doesn't need the number. Yeah, so the view doesn't work for you either, no?
No, I'm fine.
Yeah.
Yeah, but if
Okay, then
everything
you can just click on the atoms
Instead,
and then you change the right. So you click on this change here. Some, yeah, there's this change here.
Instead of deciding change.
Okay.
So this online one, this skill,
No, because this function doesn't exist.
Whenever you say code one, you will show you the suppose that you want
No, you click it again. So 2 times, and if you click it even more times, it pops up with a pop-up. Yep. Johnny, did you try the NGL viewer in the Mac?
Yeah. No. Yeah.
It works. What's the problem? What was the problem?
Yeah, I will.
This is a matter of
It's basically in my voice this way.
It's basically
again, it's probably
change my view.
Just
Just it's a string.
yeah, I don't know stuff here. But it's already done because I was always a good thing. So it's
now from HQB No, it's okay. It's gonna give you the license agreement.
I'm trying actually.
Okay, put your makeup costume maybe.
Almost
Because we don't know later action. We're not looking at also give an error like okay, so going
oh, maybe I have to go
He finished his science. It's based on so that's the Sega did it? Did you do the Sega What's the actual what's the one? Yeah. That's Sega one. It should be like C out. Same protein core, but then you define protein as
So,
but you already defined that as B1, right? Oh, okay. So one is you put it down. What's the atoms? Then you have to say chain. Oh yeah, it's yeah. But if you want to say I want to make a chain. But it really doesn't matter, right? I don't think just the average. Yeah, I think you don't need an answer selection for that. I prefer P1 and P2 because my issue. Okay, yeah. No, I just say a protein, it doesn't matter.
I suspect the issue is
well, it works
you're the first person who's ever had that. Starts like this.
What's the active selection?
Stefan, can you come here and
as well?
it's already this doesn't seem too short.
Yeah. It's actually there.
No.
No, because
Actually,
Well, I know it's this year.
doesn't matter because it's just selecting all the
Yes, you move like here. Yes, that's fine. Removing
It's removing the side just keeping the backbone and leaving it in the name. It works.
So it's not only again our name. This is
also mutate.
two is faster.
Yeah.
Okay.
Do it from the beginning, calling it only once, because there might be a problem later.
I would do. I made again all this.
Yeah, no, it's normal because it moves the side chain, so it removes the atoms. So it removes some atoms, but if you call it multiple times, I don't know why it would remove more and more.
No.
Only one.
You can remove
Okay. So there are a lot of commands in this build thing, but first you can imagine GPCR. You can imagine that you can simply take all of that, make it into a function, and say this is the GPCR I want to build. So you can automate a lot. You can build protocols which you then use. For instance, there is somebody in your group which knows how to program. And if you want to build 50 GPCR, you just take them from OPM and you create a function that just embeds all of that. And you will see more out of them. So it will be just a single line, really, of protocol if you want to solve a program.
You just need to give an error. So that's
There is food outside. You have to feed. You'll be there only for 50 minutes.
That's it. Yeah, that should work.
It seemed to be interesting to food, but that's
If you want to learn the PDB, and learn it directly,
So I have actually, I
No, I don't see myself. Here, maybe here.
Muy profesional esto, ¿eh?
See if it's finished executing action. Because Johnny needs this for his presentation. Yeah, I think it's finished. Yeah, okay, it's fine. Avstrals, ne? Avstrals, no. No, Avstrals, no. Sí, Avstrals. Espera, espera, ven. ¿Cuántos venía a conectar? De 1:30 a 2 días. Y ahora